Hello everybody, welcome back. Today we're looking at 6.4 optimization problems 1, creating the model. So in an optimization problem, the objective is either to find the maximum or minimum value of a quantity, or how to achieve the maximum minimum value. One method we use to call this is actually called linear programming. Okay, so we have some terms here. First term we're going to look at is called the objective function. This will be the quantity we want to maximize or minimize. It is dependent on all the other quantities. It's its own equation that we use at the end, and we'll see that when we get to an example. The constraint forgot the I, sorry. A constraint is a limiting condition on the objective, on the quantities of the objective function. So, in like that last example, you can't have less than 100%. So it had to be a whole number. Okay? Or to be 0 or above. A linear inequality will model the constraints of these quantities, and we'll show you those again when we do these. The constraints will produce a system of linear inequalities that will shape we call it feasible region. So the feasible region is the region that will work under all constraints. That's basically the part that you can shade that is overlapping all of your inequalities. Okay? Let's take a look at the example. Example number 1. So 3 teams, so that's important, so we can underline that. 3 teams are traveling to a basketball tournament in cars and minivans. So cars are also important. Minivans are also important. They're going to represent your X and Y. All right? So first, we'll look at what are the inequalities and what they represent. So let's state them first of all. Okay? So state the variables. So I'm going to let X equal the number of minivans, and let Y equals the number of cars. So remember, since you're dealing with vehicles, it'll have to be 0, 1, 2, or 3. So that means that we can write the domain and range. So the domain is X, is an element of the reals, or sorry, the whole numbers, my apologies. And Y is also an element of the whole numbers. Okay? Again, because you could have 0, you might take all minivans, or you might take all cars. So it's going to be 0 or above. And it can't be real numbers because you can't have decimal vehicles. It has to be a whole vehicle. Let's look at some of the constraints. So it says we're not going to take any more than 4 minivans. So the constraint is going to be X has to be less than or equal to 4. There's one constraint. And it says there's not going to be any more than 12 cars available. So that means that Y has to be less than or equal to 12. Okay? So remember, there's 3 teams, and each team has no more than 2 coaches and 4 athletes. So that means that we're going to take 2 plus 14, add them together, and then we're going to multiply by 3, and that's going to give us 48 people, right? Because that's going to be the only people we need, right? When we look back, oh yeah, we got to figure out how many people we're going to need for this. So the 2 coaches plus the 14 players, that's 1 team, multiplied by 3 teams total, and that gets us to 48 people. That's important, because then that tells how many, because we can get a certain amount of people in each vehicle, right? And another constraint is that each car can take 4 people, and each minivan can take 6. So this inequality is going to be 6 times the number of minivans, plus 4 times the number of cars, and that has to be less than or equal to 48, right? Okay? Because it says there's no more than that many people. So there's not going to be any more than 48 people. 48 people is the max. So that's why we use less than or equal to. You could take 48, but that's going to be the absolute maximum. Now keep in mind that you can't go negative. So that's why I have my graph only showing quadrant 1 where all the values are positive. Because you can't have any negative values. That's really important that you understand that. Okay? We'll rearrange this equation for y because we're going to need to. Might as well do it now. So when we rearrange this, we end up with 4y minus 6x plus 48. And we divide everything by 4. And when I divide everything by 4, I get y. And this will be over 4. And then take the 48 and divide it by 4 and I get 12. And that slope, 6/4, we can reduce that to 3/2, right? Okay? So that's a simplified inequality. Okay? Simplified inequality. Negative 3/2 x plus 12. So there's going to be 3 equations. Right? 1, 2, 3. They're there. So this is the first 2. They were easy. And then this was the last one, number 3. And we rearranged it. The objective function is we want to know how many vehicles we're in, right? That's our goal. So we will figure out the minimum and maximum number of vehicles. So we'll say the objective function is going to be v is equal to the number of cars, or the number of minivans, plus the number of cars. That's the objective function, because we're trying to figure out the maximum or minimum number of vehicles that we need to take. Okay? Now we're going to graph the 3 systems. So we're going to graph these, 1, 2, 3, right? 1, 2, 3. So the first one is x less than or equal to 4. So this is where I'm going to go to my Desmos graphic calculator. So the first one, the minivans, has to be between 0 and 4. So it goes all the way back here, and we stop here because we don't need it. Now I can't do the bottom. There's nothing I can do with that in the program. And the cars, less than 12, right? There we go. So there's the overlapping of those 2. And now we're going to have a third overlap. And that's going to be the inequality. So y less than or equal to negative 3 over 2 x plus 12. And you'll notice that those 4 points there is the overlap right here. It looks like a quadrilateral. So there is all of your locations. And we're only interested in all of the coordinates in between those values. And they have to be whole numbers. So the first one, I have to have all the x values less than or equal to 4 like I showed on the graph. Then I did the y values less than or equal to 12. Now again, remember, I didn't go into the negative x or the negative y because of the constraint on the domain and range. It has to be whole numbers. I'm not interested in anything to the left of the y-axis or below the x-axis. So they're basically constraints as well, based on domain and range. And then my final inequality, the third one that has the slope, I started here at 0 and 12. I go down 3, right 2, down 3, right 2. I don't have to go any further because these x values have to be less than 4, so I didn't need to draw. I continue my line, and all of these are possible solutions, or possible combinations of cars and minivans that will work. Okay? So this is our first step in the next 3 sections as we continue to develop and work through these inequalities to develop an optimization problem. So this is the first step, and I hope this video helped, and we will talk again soon in the next example, when we look at example 2 on the back page. So thank you very much for watching, and like I said, I'm hoping this helps. Thanks again.